Hello, my name is Muhammad Shekarbu. I will be talking about jitter reduction of model-lacked hybrid silicon laser with intra-cavity. The model-lacked laser is a special class of laser that produces a time-domain series of short optical pulses at radio frequencies. They have a broad range of applications such as optical clocking, arbitrary waveform generation, optically sampled analog to digital converters, ADCs, and frequency metrology. Large noise figures, however, are strongly restricting their applications. For example, in ADCs, this figure shows the requirement for timing jitter of the source versus sampling frequency for different number of resolving bits. This dictates that for an 8-bit resolved ADC, the timing jitter should be 100 femtosecond or less for sampling frequency in the XQ band. Possible solutions to reduce timing jitter are hybrid modelling, optical injection, optical feedback, and long cavity. In hybrid modelling method, very low timing jitter has been demonstrated, but the required stable high frequency electrical oscillator represents a large cost disadvantage. Optical injection requires continuous wave laser with narrow bandwidth, so this approach suffers from the same disadvantage as hybrid modelling of high cost caused by external light source. In optical feedback and long cavity, without the need for external source, by adding a long delay line can achieve low phase noise. In long cavity lasers, to obtain desired high frequency repetition rate, harmonic mode-locked operation is the inevitable necessity. However, the supermode noise is a major drawback of harmonic mode-locking. Using intra-cavity fabry-pyro-ethylene as an effective method can suppress the supermode noise. Passive mode-locked lasers in silicon photonic integrated circuits have attracted increasing attention in recent years. Silicon photonic passive waveguide makes long on-chip cavities possible. In this structure, RF line widths and timing jitter are reduced. With this technique, low phase noise and timing jitter can be maintained at high repetition frequency. We extend the delay differential equation model to study harmonic modelling of the long cavity lasers. A sketch of the model setup is shown in this figure. This figure depicts a sketch of corresponding configuration. The set of three coupled delay differential equations for the slowly varying field amplitude, the saturable gain, and the saturable loss. The intra-cavity filter is introduced by coupling the laser cavity to the passive cavity. Jg is unsaturated gain and Jq is unsaturated absorption. The carrier lifetime in the gain and absorber section are given by gamma G and gamma Q. The factor Rs is proportional to the ratio of the saturation energies in the gain and absorber section. Function of R describes the amplification and losses of the electric field during one round trip in the ring cavity. Spontaneous emission is modeled by complex Gaussian white noise with a strength D. The line width enhancement factor in the gain and absorber section are denoted by alpha G and alpha Q. In this page, dynamic results of DDE model is shown. The spontaneous emission was not taken into account. This figures shows dynamic range of repetition frequency. In without intra-cavity configuration, various harmonic regimes of modulating can be obtained. All of the harmonics H1 to H10 are generated, but dynamic range of the intra-cavity exhibits only 9th and 10th harmonic region and significant increase in 10th harmonic region compared to without intra-cavity filter configuration. However, the region of continuous wave increases. Indeed, intra-cavity filter suppresses intermediate harmonics. In with intra-cavity long ring laser, only 10th harmonic component can be seen, but in other configuration, all harmonic components are apparent. This is in good agreement with experimental results. In without intra-cavity configuration, but by increasing unsaturated absorption JQ, the pulse width decreases and consequently peak of pulse train is increased. The modulating operation tends from higher harmonic to lower harmonic frequency. But in with intra-cavity structure, the change of JQ does not lead to significant effect on width and peak of pulses. In this structure, by increasing unsaturated gain, the peak of pulse train increases. By considering the spontaneous emission in modeling, the fluctuation in arrival times between pulses are apparent. This fluctuation can be quantified by the timing jitter. The single sideband phase noise of the fundamental 20 GHz ring laser and with intra-cavity configuration are plotted. It can be seen that the phase noise is improved about 10 dB. The RMS timing jitter of with intra-cavity that normalized to the RMS timing jitter of fundamental 20 GHz as a function of JQ and JG is depicted in this figure. The reduction of phase noise and timing jitter are in good agreement with the experimental results. In conclusion, the influence of the intra-cavity ring on dynamics, phase noise and timing jitter has been investigated. By DDE model, we can show the intra-cavity filter can suppresses intermediate harmonics. We find a reduction of phase noise and timing jitter compared to fundamental 20 GHz ring laser. Thank you very much for your attention.